I think you can't see this little control bar from Zoom that I rearrange on my screen, but you can probably see everything else. Can everyone hear me okay?
Yes.
Yeah, yeah, it's good. Yeah, good to nod your heads. I think there are no controls on Zoom in terms of muting and voice on this. So obviously, if we have any Zoom bombers, we'll deal with it when it happens, but it hasn't happened so far. So all right, so why don't we get rolling since it's 12:05. Well, welcome to this experimental course. 497s are, of course, experimental courses. I call it EME 497, but it's actually EGE 497. EGE is a program that, or designation that doesn't really exist anymore. It was the name of our department. 10 years ago, energy and geoenvironmental associate with your programs, I guess, rather than with a department. So many of you, I don't know what programs you're with. Are you, I'm guessing that you might be energy engineers, the majority. I don't know if that's correct. I see heads nodding. So are there any people who are not energy engineers? I haven't looked, I don't know if I can tell what people do. Who is not an energy engineer? Whoa. All right. Okay. So it's absolutely either we've got a very shy interloper who doesn't want to speak up, or it's true that we are all energy engineers. So this is a class on geothermal engineering. You probably know most of the deals. I've opened up Canvas, I guess, but I don't necessarily need to be on Canvas. I can open up probably the other screen. So if you want to find the course materials, as usual, you can find them quite straightforwardly by finding me. The first hit on Google would be my name, would be this page here. And this class has its own resources page, as we had for other courses as well. And today is just an introduction. I want to go through what resources are online, what the course is about, what the syllabus is, what I propose to do, what the deliverables would be for you. So you can decide whether you still want to be here on Thursday or whether you want to zoom off to some other location. As I said previously, I should check, I guess I need to check for, we have 21 participants. I need to, please, it's a, yeah, I guess if you are coming to the class, then please arrive promptly because you have to get admitted and I have to admit you. And so there's a chance that if you join late after I start prattling on that you may be sitting in the waiting room actually until, anyway, I'll put the participants up on the screen so that reminds me to admit people in who are arriving late. We'll record our screen captures and post them. I'll use Zoom as I did for 303 last semester. I used to use a different package to record the stuff, but I don't need to because we're broadcasting on Zoom. This is a class that's been offered once. It was offered once 2 years ago, as I mentioned. Similar form in terms of the syllabus, but very different prosecution, I would say. The prosecution was that the students basically ran the course. I gave no lectures except an introductory one, and then the students went away and made 2 individual videos, which were basically the material on the syllabus. It's arranged. I don't want to do this this year. And so the onus on me, I guess, is to be able to create the content for this. So that will be my challenge rather than yours. But there are some deliverables, of course, and the deliverables will involve presentations, as they have done in previous years. And so if you need to find the material for the course, there are 2 resources to find. One is the course resources website, oof, too big, which is this. And also Canvas, I guess, would be the other one. And the syllabus, which I have, the stuff on Canvas, I don't know that there's that much on Canvas. You just saw my Canvas, I thought you saw my Canvas page just now. There's not much on there, but there are some quizzes. These quizzes, if you have taken EME 303, are not so different from that, in that they are material related to the course. They were put together by students, as you'll see if you look at them. The quizzes were put together by the students, as you'll see as well. The 10 questions that you have to answer just to make sure that you've gone through the material. And I think if you look at them, you'll see that some of them are in different standards of quality, I would guess. Some of them are adequate and some of them are, I think, are pretty small, seeing as each of the single presentations amounted to 50% of the grade. Some of them are quite skimpy in that regard. But anyway, that's online. So that's one part of it. So I guess I'll get out of full screen. I'll bring up some other resources on the page. I guess. Ask questions if you want, please do. It's not a very formal class, as if any of you ever turned up in 303, you would have found out that. So what I'll do is go through what we plan to get achieved, get done in this class. So it's easiest to look at the syllabus. Welcome to my home. You can see, what can you see on the wall behind me? You can see a Morris Escher print. You can see, is it right? No, that's kind of interesting. Yeah, off to my left is a listing of what different hops flavors are for making beer, if any of you have ever made or drunk beer. And I'm trying to think what else is on the wall, nothing much else. Anyway, so the meeting time for the class is now between 12:01. Let me look at participants just to see if anyone else has joined. No, that's good. All right, I'm presuming everyone's here. The first 4 weeks, as you know, Penn State has put back the arrival on campus in class time until the 15th of February, in which case we'll start doing things after that. To look after your mental health, Penn State has prescribed some wellness days where you can't have classes. 2 of them fall on one on a Tuesday and one on a Thursday. So they're the only 2 that affect us. And so we'll figure out how to get around that. And so we'll live by that rule, I guess, and have classes online until the 15th. I might do it until the week after that. I planned all this with, I think we did with 303, right? We had a week of quarantine before we went into the classroom. And that was prudent. Maybe it's not necessary now that we're having 4 weeks of quarantine, but I thought we would do anyway. That's the plan. We don't have a room yet, but there will be a room on campus in due course. The Zoom room you must have found. You might be able to do the same thing. You can actually define your own Zoom room. You probably get a Zoom room with Penn State, your Penn State status. You can name it anything you want, and it will use the same. Do you have an undergrad, as an undergraduate, do you have a Zoom room? Yes? Yeah, well, if you do, you can name it after yourself, just as I have. This is the same, I guess it's a 10 number identifier, which is the same as a telephone number. Just doesn't happen to be area code 814, but my Zoom room number for 303 or my Zoom room is a 10-digit number. It happens just to be a telephone number that you can dial into if you want. There are a couple of resources. I don't think you need to look at them. They're both meetings about geothermal energy. One in Cleveland. I guess I can, if I, how does this work for me? If I do it, I can go, if I look at this, I have this thing up, a bit cumbersome, but it's from a meeting, Geothermal Energy, that was held in Cleveland, February, 2 years ago, 3 years ago. It has a bunch of presentations. And actually, it was probably the genesis of me doing this course on geothermal energy. Perhaps it was in 2009. I can't see the date on it. And because the reality is for geothermal energy, clearly it's a renewable form of energy. But for a student taking a class in geothermal energy, it really is a niche market. So the interesting parts of geothermal energy are big geothermal plants that sit on plate boundaries, like the geysers in California, just north of the Bay Area. But there's really not much work in those areas. And a lot of people who work in that area would be petroleum engineers because the discipline is very similar. But at this meeting in Cleveland in February, I think of 2019, well, it must have been 2018 perhaps, I found out that actually there's a big market for jobs in what I think of as a more mundane area of geothermal energy, which is the home heat pump, the ground source heat pump area, and which I think there's a big consulting activity in that. So there are jobs for energy engineers for someone who would take this class. And so that was my impetus, I think, to actually give a course on geothermal energy, because I thought it finally might be of use and of interest to a number of students who could then parlay their way into that discipline. So anyway, this is just a listing of a whole bunch of presentations. I think they're just recorded presentations of this meeting. Yeah, you can see Stuart Simmons, who's a colleague of mine at University of Utah right now, gave one of them, etc. And there's one from me there as well. So that was one reason for doing that. Actually, that might have been a different meeting. That might have been this meeting in 2013 in Salt Lake City, which is different. So the Great Lakes Said Heat one was the one that I was interested in, because I found out that there's this whole new endeavor and consulting industry related to looking at home-sourced heat pumps, designing them, putting them in, thermal storage for big buildings, where all these big tech corporations with lots of money to spend and wanting to be environmentally responsible put subsurface chillers in to be able to run air conditioning and to be able to reduce their environmental footprint. And so that was perhaps the impetus for this. And so there are some resources for you based on that. So the design of the course is based on a few texts which are present within the EMS library. I guess I could use my pen, just like I have done for other things. Huh? You're used to seeing this, right? For sure. And so most of the texts are in the library. They should be on the second page. Actually, I think, I'm not sure whether I should say this too loud, I think you can find them. I found them for free online. The one that we'll use mostly is Glassly, I think. The one that we'll use second mostly is Grant. And the one that we will use that really addresses the heat pump one in the latter part of the class is Rosen and Kui-Fai. And so as far as I know, all of them can be found online. I won't serve them available to you, but I'll let you find them. Let me know whether you do find them, if you don't find them. But they are purchasable books. They can be purchased, but they can also be found legitimately without using, Foursquare, is it, or some of these file sharing sites that are borderline legit, illegit. You can find them just available. So that's where I got my copies from. So my copies are here. This is, I think, Glassly's book. Bill Glassly used to be a scientist at Lawrence Livermore Lab, among other things. I guess I know of him from that. Malcolm Grant is a New Zealander who I think has a PhD in math from MIT, but still works in New Zealand. He's probably late 60s, 70. And both of these are kind of hydrothermal, deep, hot geothermal energy engineering resources. And the final one, I think, on there. The other one is Rosen's book, and that's also available to you as you wish. And so as you look through the syllabus, then the syllabus is defined relative to those books. So Glassly's, Malcolm Grant's, and the Rosen book in the latter part of the class. So I think the resources are available to you. They could maybe in the EMS library, may not be the most convenient place to get them, but I think they are available to you to download. My office would be in 231 in a normal year, but I guess tomorrow is the anniversary of the first COVID patient in Washington State. And so we're not there for the duration this year, but I would like to see you if we ever get back on campus. I presume we will in 4 weeks' time. There are no prerequisites defined for the class. I don't know if you can actually for an experimental class, which a 497 or a 597 is. But the good background for this would be 303 for fluids, because we're talking about flow in the subsurface. Thermodynamics is an obvious part of it because we're dealing with phase changes in some of these reservoirs. And I suppose another one which isn't marked here would be heat and mass transfer, which if you're energy engineers, you probably have taken or are taking or will take. Used to be with Angela Luking, but maybe it's with Derek Cole now. Is it? Are some of you taking that class? If you're energy engineers, are some of you taking that class now? Yeah. So that would be background. I forget the number of it. The deliverables for the class are, well, let's preamble this by saying I don't want to grade anything. I don't want to give the impression that I'm a lazy professor who doesn't want to do anything, because I've got to actually make the material, which I don't yet have for this class, but I don't want to spend all my time grading. There's nothing I hate more than grading stuff. And so last year with 303 was perfect. I don't mind writing solutions and putting them on Zoom for our automated exams, but to me, grading is a terrible chore. And so this kind of scheme of evaluation is based on stuff that I'm not sure that I really have to grade. So the deliverables are this. These pre-existing videos are put together by students in 2019. They submitted the videos, and they also submitted 10 questions to go with their videos, which I put online. So 40% of the grade is by doing those. They're synchronized with the 12 or so topical areas of the class, and they're served to you on Canvas sequentially, with week by week, I guess, as you go through the class. So that's a decent part of your grade. It's trivially easy, I think. So it's not very difficult at all. Participation and attendance. I hate taking attendance, and I don't think that any course should be based on that, but I'm forced to kind of go into that mode just because I don't want to grade things that you're doing. And so we will have some kind of attendance. I haven't quite worked that out yet. Canvas records people's participation in terms of how long they're logged on, or I might just choose a minute or a time within the class period to see who is still on and sharing their faces with me, and mark down those people. And that would be the participation. Attendance, I guess, rather than participation. As you may have noticed in other classes, I don't want to prattle on too much. You're welcome to break in and make conversation, but you may have noticed that I'm not a big one in terms of setting up a class for lots of participation. I talk and hopefully talk about something useful and have interactive stuff that we use, kind of a whiteboard in our stuff that is kind of participatory, right? It's not just PowerPoint slides, it's something a little bit different from that. And so that's what I think of as participation. So it's really going to be attendance, no clickers, no. I don't think I could do an online poll for who's available at certain times, but I don't really want to get into that. I want to be a bit more mature than that. I'm going to get each of you to define at least one project in a topical area of your choice, and to do it individually. So along the lines of what we did 2 years ago, one person per presentation, and also supply me with 10 questions that come up with that. And then you're going to post that stuff. I'm going to post your questions on Canvas, and everyone's going to do them for this ultimate goal. So I think it's not a difficult class to survive in, because I'm kind of feeling my way through it, because I still have to create all the material. The reality is that I actually know quite a lot about geothermal energy because I've been working in it for 30 years, but all in deep geothermal, nothing in heat pumps, nothing in aquathermal storage. And most of it is in deep geothermal that will do that, but I don't have material that's pre-prepared. But it draws on a lot of the other classes that I teach and other stuff that I have available. So that's the kind of background in terms of the deliverables. The books are online. The class material is in terms of these 3 texts that we have that are available to you to be able to put together your material. You probably don't want to use those exclusively. You probably want to use other online researchable resources, of which you can readily access online these days. And the topical areas, I think, are those which are identified here. As I mentioned, I would say that the majority of the class, the first 10 topics are on what I refer to as deep geothermal energy, the stuff that you think of when you think of Iceland, when you think of the Philippines, when you think of Central America. All of these, think of Japan, all of these places that sit on plate boundaries and therefore have very hot water relatively high in the Earth's crust. And it's only the latter part of what we'll deal with. We'll switch into dealing with these low temperature resources. So the stuff that you can put in your own back garden, which go down maybe 10 feet to get below the frost line, where the temperatures swing from cold in the wintertime to hot in the summertime. But once you get below a few feet, they're relatively constant. Ground temperatures around Pennsylvania and most places would be of the order of 10 degrees centigrade or 55 degrees Fahrenheit. And you rely on that heat to work as a source for heating from the much colder air temperatures in the wintertime and for cooling from the much hotter air temperatures in the summertime. You use that with a compressor to be able to utilize that as a place to reject heat. So that's the format of the class. So the topical areas, well, today's the introduction. It's really just syllabus, but I think on Thursday we'll talk about, have a little romp around the world to maybe look at some different sites, just because it's kind of curious and to kind of put this in perspective. We'll talk about thermal energy being developed in the Earth from radioactive decay and how that manifests itself at depth and also in the shallow surface. We'll talk about thermodynamics because we need to understand that for looking at heat engines. We need to understand something about that for changes of phase, which might happen when you recover liquid water from the subsurface and you flash it to steam in a turbine. That phase change is something that you recover power from. And also related to things like the thermodynamics of cooling waters and stability of minerals is one mechanism by which scaling occurs within pipes. And so we need to understand something like that. We'll talk about subsurface fluid flow. Geothermal energy is great. We have heat within the crust, but it doesn't do us any good unless we can use it to reject heat into, or reject cool into and recover heat from. And usually the mechanism that we do that is we use a heat transfer fluid. Sometimes that fluid is recovered hot and used by us and then re-injected into the subsurface to recover the geothermal heat from that native heat within the fluid. And sometimes we have closed systems that circulate water like in a car radiator and take the heat from the ground just by conduction, with none of the fluids actually going from the closed system into the ground and none of the fluids in the ground going into the closed system, but just merely using this as a geological radiator to recover heat up to the surface and to use it for heating. We'll use simple quantitative models, kind of box models, to look at how much heat you might be able to recover from a system, how quickly you might be able to recover it, what the piping has to be able to make that viable. You know, one of the numbers that's always talked about for a geothermal site to be viable is to be able to recover something like 100 kilograms per second of water, which would generate 5 megawatts. And you need that in one well to be able to make the system viable. And the reason you need that as a minimum productivity is that gives you 5 megawatts electricity per well. and to be able to pay off the $10 million that you might have to pay to put that well in over 30 years. That's the kind of payback you need. And so we can talk about the bottom line recovery magnitudes of heat that we have to be able to make these things viable. It's important to know something about the chemistry of geothermal fluids, because if you recover these from the subsurface, then they might completely destroy your surface equipment by fouling with scale, the deposition of silica or calcium carbonate in the piping as you go from a high pressure, high temperature fluid to a lower temperature, lower pressure fluid within the equipment on the surface. And we want to know how quickly that might occur and whether it's a problem. Also, if you're using the permeability of the material in surface, in other words, injecting fluids in one location, pushing them across your reservoir, injecting cold fluids, circulating them, and then recovering them, heated up and taking them up to the surface, we might also be worried about whether we would seal the reservoir and stop the permeability from allowing the fluids to traverse them. And if that happens, then we have to provide more pumping power to be able to push the fluids through, and we may hydraulically fracture it, and we may cause induced seismicity, and we may end up with lots of nasty environmental effects that we don't want to have. And actually, a large number of deep geothermal projects around the world, Basel in Switzerland, Pohang in South Korea, have been completely shut down and abandoned because they've spawned earthquakes. Pohang was 5.7 magnitude, killed nobody, but caused a couple of $1 million worth of damage. Basel in the Jura in Switzerland was a magnitude 4 earthquake, shut down. I think knocked some chimney stacks off, but the bottom line was that it ultimately completely shut down the project. So the imperative in developing these systems is that you don't have any negative environmental impacts. Earthquakes being one of them, pollution being the other one, and we'll talk about that in due course. Again, for deep geothermal resources, we'll talk about resource exploration and characterization, and that involves understanding something about geology, using geophysics to prospect for where the resource is and what the permeability might be, managing the rates at which you might want to take fluids out and remove heat so you don't deplete the reserve, but whether you can also actually get fluids through the reserve to be able to recover it. What methods you might use to drill down to 5 kilometers, which is what the depth is that you're talking about for some of these systems. How you interpret the results of both the drilling and any measurements you make in the very expensive hole that you make that might cost you $5 million, $10 million. What those downhole measurements would be, I guess. I suppose interpretation of downhole measurements should come after the downhole measurements themselves, and what measurements you can make during drilling, how you complete the wells meaning how you put casing in them. Most geothermal wells, because they're very deep and quite hot, most specifically because they're very hot, they have what's called a barefoot section. And so you drill down 5 kilometers, the first 2 or 3 kilometers might be cased with steel casing so that when you inject the fluid, it goes down to the zone that you want and doesn't go anywhere else. But the lower part, because it's very hot, is very difficult to put casing in and to seal with cements, because cements don't work very well at maybe 200 degrees centigrade. What's that, 350 Fahrenheit? I don't work very well in Fahrenheit. So at that heat, and so the bottom part of the well is so-called barefoot typically. And the question then is, how do you recover fluids from that region? So you complete to a depth, you don't complete before it. You probably all know that the shale gas revolution that's really spurred the Pennsylvania economy in the past decade, I would say, since the early 2000s, has been the result of 2 innovations. One is drilling horizontal wells, and those wells are usually cased their full length, and then that casing is blown apart by shape charges to get through the casing into the formation, and then you hydraulically fracture it, massively hydraulically fracture it. And so those kinds of innovations are also possible innovations to be used in deep geothermal energy production. But it's not quite as simple as that, as we'll find out, because having a very fast through flow conduit where you can get lots of water in or lots of gas out in the case of shale gas doesn't necessarily mean that it's a very good heat exchanger. So a single conduit that goes straight through a reservoir is a very effective flow conduit to allow you not to spend much energy in pumping fluid across it, but fluid will go through it so quickly that there's not much heat surface area. And if there's no heat surface area, then it doesn't work very well as a radiator in your car, which of course has a huge heat surface area to be able to cool the engine. And so we'll talk about understanding methods of well completion and how we calculate permeabilities, how we calculate heat recovery, etc. So that's the kind of background, I guess, up to that point that we need to be able to be useful in talking about these so-called deep geothermal resources. And then we divide into three areas. Two really, I'd say, hydrothermal and what are called enhanced geothermal systems. So hydrothermal reservoirs are exactly the places like the geysers in California, the Philippines, Iceland, where there are existing fluids that are high within the crust in a plate boundary, close to a plate boundary, where because the plate is deforming, there's lots of strain. That means that there's lots of permeability. And so you just stick a hole in the ground and you can suck the fluids out, and you're almost guaranteed that you'll be able to produce fluids from that. And they'll be hot, and therefore the geothermal field is a no-brainer. It can work. You can prospect it. You can find it because there's springs on the surface, hot springs, and therefore it's a no-brainer. The holy grail of geothermal energy, I think, is what people have been looking at for the last 50 years. From the very first project at Fenton Hill in New Mexico at Los Alamos National Lab, which is what was called hot dry rock geothermal, which is now renamed as enhanced or engineered geothermal systems. And the idea is that even under New York City, you can drill down to 5 kilometers. We know that it's going to be hot at 5 kilometers because we know the geothermal gradient is something like 25 degrees centigrade per kilometer or 50 degrees centigrade per kilometer in the high heat flux area. So you're guaranteed hot rock at those depths. You put down a second hole and you want to use it as a big geological heat exchanger to inject cold water and recover heated cold water as it traverses across the reservoir. And so the unknown in that is whether you can make this reservoir that will allow you to flow fluid across it at this depth, which will allow you to recover the heat from it. If you can absolutely solve all of our problems on this planet with geothermal energy, because the resource is so huge compared to our consumption. And we'll talk about that in due course. And so EGS, I think of, is the one that I'm particularly interested in and have worked on it for, I guess, actually since 1986 from the projects that were around. So long time before you guys were born, and it still continues. And so right now there's a plan to build an EGS at Cornell. This time last year, maybe a week earlier than this time last year, there was a meeting at Cornell looking at using an EGS system, drilling a very deep borehole on campus at Cornell. They used to burn coal and had a coal plant, just like Penn State did with the stack, which is now demolished. Penn State also switched to natural gas. Cornell also burned natural gas. And now they want to use deep geothermal, in their case, as direct use. So not to generate electricity, but to heat and to cool the school. So in the same way as a heat pump, that you'd have within your house, but on a much different scale. And so we'll talk about these methods. Hydrothermal is plate boundaries. Not so many jobs in that. EGS perhaps is even more researchy. I think both of these are very interesting. I'm looking out of my window here I live on 10 acres and we let a guy hunt. He's just walking up the driveway past my window to sit in a tree stand for the rest of the day, I think. So EGS, I think, is a researchy one. Direct use is also researchy, but is using this deep geothermal energy. And the final part is to then look at, whoops, I guess I didn't mean to do that, is to look at where the jobs are. And I don't know if it really will be time-wise, basically 1/6 of the class, which is 2/12. I think it might be a bit more than that, but that's where the consulting work is now. And so the mechanisms behind ground source heat pumps we'll talk about for heating and domestic heating and cooling of both domestic residences and also on a larger scale well fields that get put up by Google and wherever else to be able to take advantage of the subsurface as a heat sink for air conditioning and a heat source for heating in the wintertime. So we'll talk about that in due course, so-called low temperature resources. And we'll also talk about underground thermal storage, which I think is related to this. Maybe it can be slightly hotter. And so the other thing that the big issue in terms of renewables, certainly those which have intermittency attached to them. So wind and solar only happen when the wind blows and the sun shines. And so at nighttime, obviously, you need some kind of storage to be able to store PV energy. So that could be big battery banks, such as Tesla in the Arizona desert, is it, or the Nevada desert, to be able to store energy. One method of being able to store energy is to pump hot water into the ground, keep it in the ground, and then recover it and use it at some other time when you need it on a diurnal basis, not necessarily on a seasonal basis, although it could be a seasonal basis as well. So in the same way that pump storage schemes where you have a reservoir, when you get cheap electricity at nighttime from nuclear power, you pump energy up to the upper reservoir. When demand comes at 7 o'clock in the morning for everyone's toaster, you run it down through the same pumps in reverse to generate electricity, and you use it as a method of being able to store energy on large scale. And so we're talking not in small batteries on a Tesla. I think even a Tesla is a chassis that's made out of all of these D cells, right? The D cell batteries that you can buy and put in a flashlight, a whole bunch of those which are just made integral into a car. But that's the background for these battery packs. So that's kind of the background. So most of my interest in this is deep geothermal energy. That's kind of the focus of the class. I think that's the interesting part of the class. I don't think that's where the jobs are. I think there are not so many jobs that are in that area. I guess I have your pictures here. I thought there were some things on the right-hand side. No, I don't see them. No, that's interesting. I thought I put down some people's names on the left-hand side in terms of people I was going to invite to talk to us. And I mention that because one of the ladies, we, in the last 3 years, but canceled last year because of COVID, we run a class, not this class, that is a travel class that goes to New Zealand called Sustainable Energy New Zealand. It's a little ironic, the fact that we travel 6,000 miles and probably use up a ton of CO2 per person to get there on planes for a class in sustainable energy. But we used to go and visit Waraki, which was the second geothermal site on the planet after Lardello in Italy. And now at the place that we would visit, which was called GNS, which is Geological and Nuclear Sciences, which is the equivalent of the US Geological Survey. It's basically the New Zealand Geological Survey. They run an office out of Wairaki in North Island. And one of the people working there is a former Penn State graduate in earth sciences. Her name's Lara Owen. We ran another travel class in 2003 that she participated in. That's how I know her. And she also participated in a drilling program in the Caribbean for another project that I was involved with around that same time. But anyway, I was going to have 4 people come and talk to us in this class. Lara is one of them. She's a geochemist. She got her PhD in geochemistry at New Mexico Tech. I haven't asked her yet, but I hope that she'll talk about geochemistry when we talk about the geochemistry of fluids here. Another guy was Justin Pogacnik, who's a PhD from Duke, who was also working for Mercury. Actually, that's who Lara's working for. She wasn't working for GNS, she was working for Mercury. And I was going to ask, although he's moved away, I was going to ask if he could talk to us about reservoir engineering and subsurface reservoirs. And the two other people were either Will Pettit, who's the executive director of the Geothermal Resources Council, someone about the same age as me, who's a geophysicist who will talk about drilling and completions, if he'll agree. And the other person I'd get to talk in general about hydrothermal power, and his name is Greg Bignell, who's a Brit, who's now been living in New Zealand, did his PhD in Japan on geothermal energy, and he would talk in general about geothermal energy in New Zealand. And he's already offered to do that. So hopefully Greg will do that. So I still have to contact those people, but that's at least one of the plans. Other stuff, well, academic conduct, we don't have to talk about that. You all know about that, and you all know to do your own, to work together, but submit your own work, of course. Some other random things that I've only put in since COVID. I never lived by this. The syllabus you get today should be roughly the syllabus that you live by. The grading scheme, I don't think will change from that. And so, yeah, the syllabus won't change. It'll change trivially. We were asked by our college to put a whole bunch of stuff in our syllabuses, so the syllabus actually becomes a book on things that you should and shouldn't do. And so if you want to visit those things, they're on that add-on, which is online. You can access to that. I don't expect it to be a particularly draconian class. 303, if you've taken that, you know that we don't change grades. They're very defined in terms of what you get on the tests and what you get from the quizzes, and that they are what they are, and they're not massaged in any way. And so I imagine people's scores, they were very high actually in 303 this year, higher than usual, but I expect the scores in this class to be moderately high, because I think of it as a practical applications class. 303 fluid mechanics is kind of a gateway class into the major. You've passed that muster with that. If you pass that class, you're beyond that, and now you should settle into some courses that actually might make sense in terms of the major that you've chosen. They might start looking like things that you'd like to do in your professional career. And so I think of this as a tools class in terms of understanding something about geothermal energy and what you might do is if you work for a company. And so my ambition for this class is that you take away from it some information that is actually useful to you once you go and work for an employer, so that the employer doesn't have to educate you, train you, whatever you want to call it. I prefer educate in the things that you would do for them that would make money for them if you're working for a consultant, etc. A rough outline of what we'll do is in this. You'll see that here there are 12 topical areas. That they're the same topical areas that are in place. Okay, all right. These are this is Justin Pogacnik. This is Lara Owens. This is Will Pettit. And this is Greg Bignell. I guess I'd forgotten where I'd put those. And so I'm going to try and get those to come and talk in one of our meetings around those times, if they'll agree. Zoom is a great thing in terms of that. Obviously, they're not in the right time zone. I think for Greg and for Lara in New Zealand, 12 o'clock for us is 6 o'clock in the morning for them the next day. But that's kind of doable. Justin now works in Belgium, and so that would be 6 hours behind. So that would be, no, 6 hours ahead. So that would be 6 o'clock at night. So anyway, we'll sort that out. So the color coding on this, these are wellness days, where I guess we don't have classes for our 2 Tuesday and Thursday meetings that occur on those. But I'll figure on giving you something to do if I have something to do. These other ones are timing for deliverables. And so the deliverables are really the deliverables that I mentioned earlier. And that is really, you'll do these videos probably one per week. In some weeks, I think in terms of drilling and completions, there's a whole bunch of them to do, but they will take no time. I think the people who are putting together this material, the students, some of them are really very short, and the questions, as I remember, were not particularly challenging. And I hope that you will do much better when we talk about the things that you will do in this class. And so my thought is for this, that Amber Alert. Yeah, an Amber Alert. And so nothing that I need to worry about right now. You might have got the same Amber Alert if you're on Pennsylvania or a center county network. Yeah. Back to this. Where are we time-wise? Yeah, actually, I'm talking much more than I should. So there is one real deliverable for you, and it's for an individual presentation. And it is on a topic of your choice, and it has some structure to it. And it's always good, I think, to have some structure. Let me see if there are other participants I should welcome. No. So I don't worry about that. And so today, well, nothing. So I'm going to ask you to define a topic. So you need to figure out a topic and to identify what that is, and then to submit it. So one of those round circles would be the first one of those. This must be the first deliverable. To prepare a plan for the presentation so that you actually do it. I know it's tough to have a single date that you have to get everything done by, so I'm not taking that route. I'm going to get you to do things incrementally. Again, to submit that online and get some feedback. Prepare and record prepare the presentation in PowerPoint format. Again, submit the PowerPoint, narrate it. And so if you haven't, well, you should have done this for 303. So you can narrate it just by recording into PowerPoint. You can use other fancy ways. You can record on Zoom. You can do all kinds of things to narrate it and to store it as a video, and then to upload it onto YouTube or some other site so that I can link to it. And then based on that, you'll also prepare 10 questions, multiple choice or more involved questions. The more involved, the better, I think, to test your colleagues. And I will then post those on Canvas. And then in the final 2 weeks of class, every student will end up taking them. So that's the basic outline. So that's the plan. I don't know what to say other than that. I guess the other item of interest should be that it's easier rather than say 5 pages, 10 pages, it's easier to say narration for 20 minutes. And so that means not sitting in silence for 20 minutes, but having some substance. That's the easiest way to do it. I'm not a big believer in saying that a presentation should be how long it needs to be to get your point across, not artificially some length, but it should be 20 minutes just to make it sure that it's a worthwhile endeavor to account for the grade that you get in this class. So that's the background for that. Yeah, you can guess what the things, the reasons for this is to encourage you to explore something, to think critically, to demonstrate an understanding. There's no better way than teaching a class and having to stand in front of people, even if it's on a recorded basis, to make sure that you know what you're talking about and you're not spinning a yarn when someone says, yeah, but what about this? And you don't know what you're saying. So it's there's no better way than to present stuff to make sure that you really do know something. And also ultimately in the other quizzes and looking at the other videos are to actually learn from what the other students have been talking about, to reinforce perhaps the topical areas. So I don't really have an idea yet on what the topics should be. I'm not going to prescribe them. At some stage, I guess it could be that I need to do that. I would imagine that the topical areas are relatively well laid out with these resources, that it's not going to be difficult to be able to explore exactly what those are. Certainly the course resources page contains the student presentations for all of these topics from the past. But as I say, I don't think they're necessarily a shining example of what you might want to aspire to. In terms of the other stuff, the designations for this is online synchronous. This is in class synchronous. I don't know if we'll have the first class as a quarantine class yet. We'll see, but we'll update that as in due course. And the other part of the presentations is there is some structure to it. Just as if you took for 303, there was some defined component. The structure is things that I think are important. Why is the topic that you're going to talk about important? Why should anyone care about it that's listening into it? What are the scientific questions that you're trying to address? What's the scientific background you need to this? And then to explain what the topic is, I always encourage people to do something quantitative. One of my favorite quotes is by Kelvin, as in the guy for whom degrees Kelvin is named after. And it is, if you are to say something important about something, then if you can calculate something around it, then that really is saying something about it, not just arm waving, talking about hypothetically, it could be this and work this way. If you're able to put some numbers on it, then you really do know something about it. So some kind of hand calculation and a case study, if it makes sense, and then to conclude. So it's pretty standard outline, I think, if you want to be able to make a case for regular presentation. It should have an objective, it should have the body of what you're talking about, and it should have some kind of conclusion. Recording this stuff, you can record it directly in PowerPoint, and you can convert PowerPoint directly to MP4 or .mov files, which are then YouTube uploadable. And so that's probably the easiest way to do it. But there are lots of other ways to record this as well through open source software that can be available online. So that's kind of it. I don't know. I don't have much more to say other than that. So as you know, if you've been in class with me, I can talk forever. I think it's interesting. Again, it's interesting to chart a life through academia. I started teaching, and it was Penn State was my second job. But when I started teaching, I was 26 years old. So I was 4 years older than the kids in the class. And so at that stage, you don't have much experience. You haven't worked on many projects. And so maybe you're book smart and you're working for all these things and you're doing this stuff. And as time goes on, you can perhaps get a bit more flowery in your language and hard waving, etc., and can talk about lots of things. And I think I'm not quite at the end of the rope yet, but I'm partway along that pathway from the very early stage to a later stage before I'm dead. And so anyway, so does anyone have any questions or want to make any comments? Remember to take your buttons off mute if you're going to talk. Okay. So typically I will join a little bit before 12:05. We'll have a class online on Thursday. I guess it'll be an introduction. I have that prepared, but I actually don't have anything prepared for anything after that. So I'll be feverishly preparing stuff. Please join before 12:05 because I don't want to have to admit people as they join. So we have 20 people participating. That probably includes me. So we have 21. I thought we had 25 people signed up for the class. I'll ask again. I'm curious to know whether everyone's an energy engineer. And so the easiest way to ask that is to know whether there's anyone in the class who is not an energy engineer. Shout, please. Okay, well, that defines it then. Either you're incapable of finding your mute buttons or you don't want to share it with me, or we know exactly what we are. So no questions? Good. Well, try and develop amongst you a protagonist that makes comments and has some conversation as we roll into the 12:05 witching hour. It makes it much more fun for everybody, I think, if there's some conversation. It's a connection for me. It's a connection maybe for you, and we'll see how this goes. So happy to see you back. Welcome back on campus. Let's hope we still have a country after 12 o'clock noon tomorrow, and everything will be fine. So yeah, barring no hiccups on Wednesday, I'll see you back on Thursday. Okay. Well, we already went through, if you were at 303, we already went through an election together and the aftermath of that. Okay. All right. Take care. I'm logging out now.